Welcome back to the next video, everybody. Today, we're going to finally start proving solvable n equals 2 Langland's reciprocity, which, as you recall, is the last thing we need to actually prove to finish the proof of Langland's tunnel and hence the chapter. To do that, we're going to just start today by gathering specific instances of functoriality we can actually prove, instances which we're going to need in this proof. Okay, so the first of those that we'll talk about today is automorphic induction. So first of all, let f be a number field. And let's let K be a cyclic Galois extension of f of degree n. And we're going to let G be the restriction of scalars from K to F functor, res K over F GL1. So what is that? Define a functor on the category of F schemes, so schemes that have a structure mapped to F. Okay, by res K over F of GL1 of S, where S is just a random input F scheme, is just GL1 of S. Take the fiber product of S with K basically over F. Okay, so what's going on here? It's very simple. Basically, the F points of res GL1 are the K points of the old GL1. Okay, so F points are the old K points. You restricted scalars from K to F, you see. Okay, now let's let G prime just be GLN. Okay. Now, G is isomorphic to a maximal F torus of G prime. This is standard, linear algebraic group theory. Okay, what is my L group here? What's the L group of G? It's n copies of GL1 of C, semi-direct product, the Ve group of F. Now, how is the Ve group of F acting on G hat here? Here's G hat. Okay, well, it's acting through its projection onto the Galois group of K over F. Well, how is the generator of the Galois group of K over F acting on basically these n copies of GL1? How are we acting on G hat here? We're just permuting, right? There's n copies of this. My Galois group has, degree n. So what do I do? How do I have my Galois group act on this? I just permute the entries around, okay? I act as a permutation. Now, let's let rho 1 be the natural homomorphism of this L group into the normalizer of a maximal torus of G hat prime, which is just GLN of C. Now, and we can use this map rho 1 to define a morphism of L groups from the L group of G to the L group of G prime. We'll call this map rho. And what should we do? Rho of G should be rho 1 of G comma rho 2 of G. Okay, rho 1 of G I defined above, so that maps L1. That maps the L group of G into the normalizer of a maximal torus here. So we're kind of mapping. To G prime hat. Okay, with this rho 1 part. But then we also need a map from the L group to the Ve group portion of the L group of G prime, right? So what's a natural map rho 2 from the L group of G to W sub F? It's just the canonical projection, right? You can just project this to WF. Okay, great. So we have kind of a natural morphism of L groups once we pick this G and this G prime to be our groups. Now, an automorphic form on G is just a Grossen character chi of K. The reason for that is you can check immediately that G evaluated at F is nothing but K star. So we get a Grossen character. Now, when a place V splits completely in K, so I take V and F and I have it split completely in K, which means there's no ramification and all the residue extension degrees are 1 for all the primes lying over V. Okay. The representation pi V, which is the representation pi sub V of chi, where chi is my Grossen character here, induced from what? Well, above chi is a chi sub V for each prime sitting above V, right? Okay, it turns out the representation pi sub V attached to that chi satisfies that the local Langland's class T sub pi sub V is nothing but rho of T sub chi sub V, okay? If chi is unramified at V. Now, if you go back and look at functoriality, the general statement, it seems, given this information, to suggest the following. And it doesn't just suggest it, this is actually true. This is a specific case of Langland's functoriality that's actually true. It's the theorem of automorphic induction. We'll call it theorem A when we reference it later. So theorem 6, for each Grossen character chi of K, there is an automorphic representation which we'll call pi of chi, of GLN of the Adels of F, whose partial L function, LS of S pi, we defined partial L functions last time, equals the Hecke L function, LS of S chi. So like the L function of chi is basically matching the L function of pi. this automorphic representation attached to chi. All right. Moreover, LS of S pi of chi is entire, and so pi of chi has to be cuspidal automorphic, as long as chi does not factor through the norm map from K down to F. Another way of saying that, though, is just chi isn't fixed by the natural action of the Galois group of K over F. Okay, so we will need this fact. The proof when n equals 2 and F is arbitrary is in Jacquet-Langlands. When n equals 3, this is in Jacquet, Piatetsky, Shapiro, Shalika automorphic forms on GL3, parts 1 and 2. And then the general theorem is in simple algebras, base change, and the advanced theory of the trace formula. It's some hard stuff. But we don't need that, actually. We're only going to actually need the n equals 2 and n equals 3 cases. So you can kind of ignore that unless you're interested. All right, so that's the end of the video for today. We're going to look at 3 or 4 other results that are specific instances of functoriality that we'll need. Starting next video, we'll look at the theorem of the symmetric square lift and some base change stuff and some Rankin-Selberg stuff and this kind of stuff. All right, so I'll see you tomorrow, and thanks for watching.